Most of us are familiar with the simple spring scales, which are easy to make and to use. These scales require a spring that deflects when a force is applied, right? And here's a really simple example I found that actually just uses rubber bands. And again, as long as we understand that there's a relationship between the deflection and the force applied, using this displacement measurement, say here, we can convey some measure of force. Even the balance scales here that we commonly use to measure mass, by comparing, say, an unknown mass here to some calibrated mass that we might place over here, say some calibration mass MC. This uses how much that known mass weighs, basically uses gravity to form a similar elastic effect, if you like. But now there's a stored potential energy, just like a spring scale stores potential energy through a passive spring. In this case, again, the balance is using sort of a deflection here to tell you when there's a sort of an equalized force application, and that way it measures force. What we're more interested in the lab this week that we're working on are really force sensors or torque sensors, and especially in electromechanical force sensors. These provide an electrical signal that then is convenient for us to measure with some kind of instrumentation. And if you look at this as a system, right, we have some applied force or torque, and the output commonly is in the voltage that then we can measure, say, with data acquisition or a voltmeter. And this is the type of sensor that we really are most interested in. These kinds of force sensors can also not only can be found in a lot of measurement and control applications, but in some common products. Most scales that you can buy. Here's a postal scale that I had, and I opened it up, and this one in fact has a little load cell strain gauge type sensor of the type that we're going to be using in the lab. And here's one that you can actually buy from an online manufacturer. These can be pretty low cost. Actually, this one is a little bit actually more expensive than the one that we're going to be using in the lab. You also find load cells, say for measuring torque on wrenches and so on. And so the kinds of concepts that we're going to be talking about in this lab and in the following videos are useful in understanding how these types of devices work. Inherent to any of these force sensors is some kind of underlying sensing mechanism, and this mechanism relies for most force sensing on some kind of mechanical compliant element or an elastic element. If you remember, compliance, SAC, is just the inverse of stiffness. So I might use those two terms interchangeably here. And remember, in the basic relationship here, of force is related to some deflection through some parameter, a stiffness parameter here, K. For example, this could have units of newtons per meter, right? And this is a linear relationship, right? Because F is linearly related to the deflection. So we rely on this basic relationship to build force sensors. And again, the basic idea is to have a way that we can detect how much that material that has a known stiffness has changed in length. So just like in the spring scale, we have some kind of a linear scale on there that we can read off force. We want to be able to detect that change. You'll see this in a lot of different types of force and torque sensors. That relationship that relates force and displacement for some sensing mechanism in a force or torque sensor does not have to be linear, even though I show a nice linear relationship here. Remember, the nice thing about a linear stiffness relationship is you only need one quantity, say, to relate how much something has deflected to the force. But if it's not linear, that's not a problem, as long as we can calibrate the relationship or understand what that functional relationship is. That's really not a problem, as long as we have that well understood. What we really need for a good force sensor is that we have a sort of what we can call a bijective relationship. In other words, if I have a deflection there's a one-to-one relationship with a force, right? You don't want something that might look, might have a non-unique relationship as shown here, right? So this, while I could give it a deflection, and this actually is bi-unique because I would have a unique force if I had a unique deflection, it doesn't work the other way around. So that typically is not a good relationship. When you have something that's this complex, it usually means that you don't have what we call a basic stiffness element. There's probably some buckling going on in a relationship this way. So as long as you have a one-to-one relationship, then you have a good understanding of that element. And also you want some repeatability because you don't want the different values giving you different force relations, right? Different force values. So something that's repeatable. Also, I'm not showing it here, but you also would like something that doesn't have a lot of hysteresis in it. So those are, we won't go too much into that, but if you sometimes read force sensor specifications, it will have values such as hysteresis on there. And remember, hysteresis is, let's say you apply a load, and then when you unload it, it may not come back until you have the hysteresis loop. You'd like sensors that typically that don't have these kinds of characteristics. So typically manufacturers will tell you that they have a minimal hysteresis due to the material properties. To give you an example of now, if you understand this force displacement relationship, you could build a sensor out of anything. So here's a little force sensor I made one time to measure, forces on a keyboard key. These are really low forces, anywhere, they peak at about 50 grams. And actually that relationship I drew is key relationships. This little, you're interested in what the stiffness of that little rubber dome is, and actually it goes up and it buckles here, and strikes here, and then it increases as you continue to press the key. So if you want to understand that or measure that relationship, you need a really low capacity load cell. I didn't have one at the time, so what I did is I found a really compliant spring, calibrated that spring, and then what I could do was measure the deflection of that spring by measuring these two motions. So I could basically measure how much that spring was deflecting as a force was applied here, right? And then that way I could quantify that relationship. So here's an example of some typical data. In fact, if you look at, this was some data that I collected. This, as I applied the force, you can see this actually had some hysteresis. I applied the force and then came back, right? There was some gap here showing that this little dome has some hysteresis itself. Okay, so again, here's to show you an example one of how you can build a sensor, force sensor, as long as you understand the force displacement relationship, and as long as you can measure the deflections. Okay. Some of the more common sensing mechanisms that you'll see in force sensors are strain gauges, which will be the topic of the following videos that I give you here. But there's also force sensors that use piezoelectric crystals, and others actually use sort of like that key force sensor that I built that used a direct displacement measurement either through contact or non-contact. So it could be optical. I'll show you some examples of that. The most common ones are of this type, either piezoelectric, piezoresistive, which uses resistive strain gauges, or other types of resistive effects. So here in this slide, I'm just summarizing for you different types of force mechanisms. The passive type are like the spring scale. Passive meaning that there's no energy required for this guy to work, right? You have a passive spring, and as long as you can measure that deflection, you have a force measurement. But then you have electromechanical types. Typically, you have to provide some electrical power for these. And you have resistive type, and here's a strain gauge shown there, and we'll talk more about those in following videos. There's also capacitive type. In this case, you want to be able to detect how the capacitance of these plates changes as you apply a force. So those are capacitive type force sensors or torque sensors. And then another type is a piezoelectric that uses some kind of piezoelectric crystal here. And piezoelectric crystals have a change in charge distribution as you apply a force. And piezo means pressure, so applied pressure changes charge distribution, and you can detect in a sense how much that changes, and then that way gives you an effective measure of applied force or torque. One thing that is kind of subtle is piezoelectric crystals don't hold that charge very well. You have to have a good signal conditioning to do that. So a lot of times I would recommend using resistive strain gauges if you wanted to measure static loads, basically forces that go to very low frequencies if they're dynamic. For resistive or even capacitive force sensors are good for that. Piezoelectric is very good for more dynamic forces that are always changing, and so those applications work. Those applications where you have dynamically changing forces are well suited for piezoelectric. These also tend to be a little bit more expensive because of the signal conditioning. Here are just some examples. There's strain gauge type force sensors. You'll see these kind of button type. They have the same kind of configuration inside as I'll show you in following slides. These are compressive type load cells. And again, you can find many types online. The piezoelectrics have crystals inside. And actually, here's an XYZ force sensor. So it measures, three components of force at this connection point here, made by PCB Piezotronics, and then I think this is just another type of piezoelectric type sensor. And here are just some others. I'm going to just show you that I have found. This is from another one of my favorite sites, SparkFun. Has a lot of different types of low-cost sensors. I think this is about a $70 load cell that uses strain gauges, and always look and see. Oh, look, I can see there's a bridge configuration here. It's got resistive strain gauges, so that's using a full bridge to within this load cell, right? So some of the slides and videos that will follow gives you insight into how this device works. Here's what's called a flex sensor, and this is also a resistive type sensor, and this shows you the instrumentation that's used. And these types of sensors that use, and it might tell you here, if you look, I'm not sure if it tells you but this is a resistive type strain gauge. And you can see here, here's the actual resistive element that's representing how the resistance across those terminals changes as you bend this guy, right? And then you might configure that with an amplifier in the output to measure the output voltage. Right, so note how there's a signal conditioning circuit. You put that resistive strain gauge in a voltage divider configuration. So you don't necessarily measure the resistance directly. You measure the voltage across the sensor resistor. Okay, that's what a signal conditioning circuit does for you. Here's another type of. I think this, if you go, this is a polymer thick film type device, but it is resistive at the end of the day. They basically put some kind of flexible substrate, and then you're measuring change in resistance, and they'll give you specifications for how much the resistance changes for an applied force, right? And you'll see somewhere in here it'll tell you, these are not good for precision. Oh, right here it says, these force sensing resistors of this type are not necessarily good for precision measurement. So if you really want more precision type measurement, you should probably rely on strain gauges or piezoelectric or even capacitive type. Finally, torque sensors can use either strain gauges and configuration structurally that could measure torque. And here's an example of actually an optical type torque sensor that has essentially a calibrated shaft, and using optical techniques you can measure how much that shaft has deflected when you apply torque on the ends, and very fine detection of deflection. You can infer rotational, right? Now you have a rotational deflection in the shaft, and that delta theta is proportional to torque, right? So this uses an optical technique.